Good afternoon. This is the Nyquist PID controller design part 3 online lab. I've ended up with part 3 because originally this lab was to be done in Newton building, but now due to the current COVID situation we're having to do it online. And so this third part is the experimental part now of the sort of results section that you would have obtained if you're in the lab doing the experiment with me. So let's have a quick recap. So the aim is to apply the Nyquist stability method to design PI controllers for a heating process, and it's a process trainer 37100 and it's made by Feedback Instruments. And the lab's been broken down into 5 separate tasks. First, to work out the transfer function. Second, to design some PI controllers using the Nyquist method for gain margins between 2 and 4. Task 3 is to use some other methods, namely Ziegler-Nichols and Turius-Lubin tuning rules. Task 4 is to, having designed the controllers in task 2 and task 3 and worked out a transfer function in task 1, is to run a simulation of the system plus the different controllers. And then for task 5, I've done this in my garage with the equipment, and I've got some real-time results which you can then compare with the simulations and then draw your conclusions and have a bit of a discussion about it. Probably better to do it the other way around, have a discussion and then draw some conclusions about it. So the first thing we're going to do is work out a transfer function for the system. Now the transfer function is a first order system plus time delay, and in this K is the steady state gain, TP here is the time constant, TD is the time delay, and we're now going to look at an open loop step response of the system, which I've done, and we're going to transfer that data then onto a USB pen. I will have put that data then on Blackboard for you to download, and then you can load that data into MATLAB to analyze, to work out this transfer function. And that's task 1, to load in a file, and the file is going to be called lab data 9, and you can put this where you like. We'll discuss that in a moment. And then to work out these parameters of this transfer function. Right, so here we have the open loop step response, and if we have a look at this now, this is the input here, which is going up by 1000, and this is the output. So it starts off at this value here, and then this is where the step comes in, so this is the time delay along there, and then it comes up and levels off like this. So if we measure from here to here, that's that distance. This will give us the steady state gain. 63% will give us the time constant, and this distance here will give us the time delay. And we've got to remember that the step input is a size 1000, so these numbers in the K direction will require dividing by 1000. So this is now the open loop step response that we're going to use to calculate the transfer function. The data I'm going to transfer from this program into MATLAB for you to do the analysis yourself. Right, so we're now into the stage of using the MATLAB program to work out the transfer function of the system. That's these parameters here. And the first thing you have to do now is go into Blackboard and find a little program called lab data 9. If you can't find this, send me an email, I'll email it to you. Now, the main trick is you've got to save this file onto, it's actually got a .mat in there. It's not good. So this is the program, and this will be the program you download. The MAT is an extension for MATLAB. Now you'll have to put it in a drive somewhere. Now I find if you've got like a pen drive which has got a label E, if you copy this into the top level of the pen drive, it makes loading it very easy. Otherwise you have to put a path in here, and it's not always easy doing MATLAB paths. So the main thing is go to the MATLAB command window and type in load labdata9.mat, and it will then load in this data for you. And then once you've loaded in the data, we're then going to use a Simulink program to identify the different parameters. There's in fact 5 things we've got to work out. 1, 2, 3, 4, 5 things. And we'll go through them as we look at the different things. So let's have a look now at MATLAB. So the first thing we're going to do is type in this load E:, and this will load in the, so if we copy that, say copy and paste it in there, then that enter, that will load in the data for you. And if you type in y_data, you'll see a load of stuff in there now indicating it's loaded incorrectly. So that's to forget about this. That's all you've got to do. The MATLAB command prompt, load that in. Then next thing you do is go and load in now a program called Simulink Modeling 2020. So it was done in 2020, not in 2021. And this now reads in the input data and the output data. And the output data is displayed on scope straight away. The input data feeds through a transfer function. And so if this transfer function now is exactly the same as the real system, these two signals will look identical. And what we're going to do is adjust the parameters of K, TP and TD until this does look identical. But the other thing is we've got offsets associated with the data, so we need to get the offsets correct as well. So the first point to start is just run the program. Obviously I've set the numbers at the wrong ones, and if we look at the outputs now, we've got 2 signals here. There's the real data, that's the data that you saw a minute ago on the rig, and this is the model at the moment. So the yellow line is not fitting the red line. The yellow line, the model won't have any noise on. The real data's got a bit of noise on. So they're not compatible at the moment. So if we look here now, this signal here, we notice this has got an offset. So we've got to bring that signal down to 0. Because if it's at 0, then for locally linearized models, everything has to start off from 0. So we look at this number here now, and we're going to change this now. I'm going to guess that's say 800 for this offset, and run again, and having a look here, and it's gone a little bit below now by about 50. So if I go back to here and change this to 750, we'll notice now, run it, you've got to run it, this signal starts at 0. So for locally linearized models, we want all the signals starting at 0. So we can do the same for this one now for the Y data. The Y data is starting off just below 200, so it needs pulling down again. So we can pull it down with this number here, and I can cheat a little bit down because I know the answers. I'm going to type in 1150 here. Run it again. Look at this. Now it's more or less starting. This is a bit more tricky to choose this one because it's got a bit of plus and minus noise on it, but I've chosen that number, and I think that's almost exactly going along at 0. So have a look now at the output. They both start now more or less the same point, but the two models are different. The K values are different, the time delay is different, and the time constants are different. So we're going to adjust now those 3 numbers to get a better fit. So let's look at the K value first. It's obviously, if we just go back to look at it again, the K value is too big because it's too high, the model's too high, so we need to pull it down. So if we pull it down to say 1.5 and run again, then it's not bad now, but it's a little bit low now, just a touch low, needs pushing up a bit. So if we go to 1.55, run again, then this looks more like it. So I'm going to go for 1.55 as my value here. Could have gone for 1.6 I suppose, but I've gone for 1.55. Next thing, so I'm going to look at this. This time delay now in the real model is too long. This is too long, so I'm going to pull it down. So if we go to here now, so at the moment it's a second, so we'll make it say half a second. And this. So now you can see it's better, but it's still not quite right. Still a bit too big, so let's try 0.4. And that one. I didn't run it. That's too quick. You've got to be. MATLAB isn't that fast. You have to wait for the little noise. Now you can see they're both more or less starting off at the same place. This is coming up quite nicely to being the same level as this. But now the time constant is speeding up, so we need to speed up the time constant. Reduce the time constant, so it needs to go smaller. So this one now in front of here is too big. So time constant we did, not the pole. So I'll make this say 0.5, shall we? See what that one does. Run that. So now you can see this is quite good. The 1.55 is coming quite good. This is a bit fast now. It's a little bit fast, isn't it? So we need to slow it down a bit by making the time constant a little bit bigger. So we can go to 0.6 and run it again. And this time you can see here's the real data and here's the model, and they're both like sitting exactly on top of each other. Well, not exactly, but pretty close to on top of each other. So at that stage now we can conclude that we've found a reasonable transfer function, which is 1.55, time constant 0.6, and time delay 0.4 of a second. So there's our transfer function now for the system. And so we can, wrong PowerPoint. So we've got this one, so we've done that now, and here's our transfer function. So this is the transfer function now that we're going to use for our analysis. K 1.55, time constant 0.6, time delay 0.4, and we can use this now for plotting some Nyquist plots to work out the PI gains for a Nyquist controller. That's what we're going to do next. Right, so now we're into task 2. Design the closed-loop PI control method using the Nyquist technique. And this is a PI controller, so this is the structure. And the one we're going to use is Kp plus Ki over S. Now, for Ziegler-Nichols and some of the other methods, they tend to write them in this form as well, Kp into 1 plus 1 over Tis. So in this case, Kp is the same, but Ki is Kp over Ti. So just bear that in mind. But for our purposes we're using this standard format. So we're now going to go on to look at designing the control system using Nyquist plots, and we're going to go for gain margins between 2 and 4. 2 tends to give you quite a fast response, and 4 quite a sluggish response. So most control systems are designed for gain margins between 2 and 4. So we're going to look at the effects of gain margins at 2, 3 and 4. If you go less than 2, it's going to get too much overshoot and too bouncy. Bigger than 4, it's going to be too slow. So here now is the transfer function we're plotting. Here's the K, TD and TP, and here's our PI controller, Kp over S plus Ki over S. In this particular case, the controller is given by, well, we have this format for it here. So what we're going to do now is we're going to put K as 1.55, TP is 0.6, TD is 0.4, and then this code here now plots this little Nyquist plot for us. So if we take this diagram, take the code, copy it, do a copy, and then go into MATLAB and do a new script and then paste the code in and then run it and just give it some name. And it doesn't work, so I've done this on purpose. The trouble is when you copy and paste, it doesn't copy and paste the exclamation marks quite correctly for some weird reason. So go back, delete that one, and just put in the normal, the key where the at and the dash is. So put that in there, and delete that one, and get that one in there. So just put the right quotes in. That's the key that has the at on, like in Gmail at gmail.com. And now it's in the correct format, so for our thing, and we can run this, and here's an Nyquist plot. Now if we click on this point here, we'll get the gain margin, so it's about 0.657, so the gain margin is going to be 1 over 0.657, so that's going to give us the idea. Now this frequency is handy to have as well, but the main one is just that gain, that number there. That's where Nyquist clock crosses from there to there is 1 over the gain margin, so the gain margin is going to be 1 over 0.657. So you could copy that, I suppose, that graph that behind the top. You could do file, and you could do or even edit, copy figure, and then you could copy the figure and paste it into your report. So that could be a handy little graph to have. If we just go back for the moment to here, so there's our graph, and we can now work out our gain margins. So for gain margin 1, it's just 1 over 0.658, which is 1.52. So then for a gain margin of 2, what we do is we halve this number. So it's going to be that number over 2, which comes out as 0.76. If we say a gain margin of 4, it's that number over 4. If it's a gain margin of 3, it'd be that number over 3. So it's quite quick now. Once we've got this number, this 0.658, 1 over it gives you the ultimate gain. That's the gain in which it's likely to go unstable. That's with the PI controller in, not on its own, but with the PI controller in. And this then gives you the ultimate gain. If you then use half of that, you've got a gain margin of 2. If you use a quarter of that, you've got a gain margin of 4. Straightforward. So you can work, so they're the gains now. And so that allows me to fill in a little table now for gain margin of 2, KP is 0.76, gain margin of 3 is 0.57, gain margin of 4 is 0.38. And my KI is set at KP over TP. This is a fixed gain here. And so TP is 0.6, remember? So as KP changes, the KI changes. So this one comes out as 1.25, 0.93, 0.625. So there's my PI gains now for my Nyquist design. Right, so the next little task is task 3, using the Ziegler-Nichols tuning rules and the Tirias-Lubin tuning rules. Now these are based on a slightly different concept, but both based still on the Nyquist plot, but in a different context. So imagine you've got a controller system under closely proportional control, and it could be stable, but it could be marginally stable, and it could be going unstable. So this is with the amplitude growing. But when you find the case where it's marginally stable, this gives you what's called the ultimate gain, and you can also get the ultimate period, which is the time across the two peaks there. And Ziegler-Nichols and Tirias-Lubin, they both based their controller design philosophy on working out this ultimate gain, which you could put by putting the closed loop system under closed loop control, increasing the gain until the output became marginally stable. So if we had a quick look at that, this would be this sort of thing here. So you'd have your closed loop system, you'd increase but proportional integral and derivative to 0, and then increase its gain until this started to oscillate like this, and then we'd know then that that value is the ultimate gain. You could get the same thing from the Nyquist plot as well. If we had the Nyquist plot, by measuring that value there of the Nyquist plot, we could get the gain margin. The advantage of the Cycle-Nichols method is you don't need to know what the transfer function is. If you know what the transfer function is, you can use this method. If you don't, you can use the other one, or you could use both just to see they both come out the same sort of values. So the thinking behind it then, we find the value of gain at which the system goes marginally stable. So in this particular case, K was 1.55, TP 0.6, TD 0.4. This is the Nyquist plot code now for the just under proportional control. So we lost the integral controller, and we're going to plot this out now and work out what our gain margin is. So again, we could copy this little bit of code, do a copy, and then we could paste it into, I don't know, got some stupid thing going up here. Let's see if I can get rid of this. I'll just see if I can go into this. Here we go. I can copy and paste, and that's the code there. This time I've corrected the little dashes here as well. And if I run this now, I will get the Nyquist plot, and I can interrogate the Nyquist plot for this point here, and it comes out more or less as 0.5. So 1 over 0.5 is 2, so that's telling us that the gain at which the system is likely to go unstable is 2. So that's our ultimate gain, Ku. It's going to be 1 over that number. So that's 2. And we also know to need the frequency here is about 1.4. So we know that the ultimate period is going to be 2 pi over 4.8. So that we know what from these two numbers now what the ultimate Ku is. It's 1 over that. And Pu is 2 pi over 4.8. So we can work out those things now for our Cycle-Nichols gains, and we could, again, if we wanted to, we could do a copy figure here, and we could paste that into some little Word document that we were doing as we went along. So now if we go to our simulation, now we could get this also from simulation, remember. So if we go back to here, this is, remember, set at 0.4. We can now set KP as, let's say, 1.5 and run, and look at the output. So it's stable. If we set this to 2.5 and run, it should now be unstable, because remember the gain margin is 2, so that's unstable. And if we set this to 2, it should be marginally stable. And that will show us by having a little sine wave type output here. So it's not quite 2. I think if I go to 2.1 on this, and we get it right, 2.1, there's a small little error here, about 3% error. You can see now, there we have the marginally stable case. It's kind of just like a repeating sine wave. So we've got a little bit of error here. Maybe my model wasn't as good as I thought it was. Maybe it's out by about between 2 and 1, but 0.1 and 2, about maybe I got a 5% error somewhere here. 5% is relatively small, isn't it? But a bit disappointing for me. But anyway, if we go below this, if we try 2.05, say, and run, see, it's just decaying. So 2.1 is what we get from this test, but from the Nyquist plot it comes out as 2. So there's a bit of discrepancy between the simulation and Nyquist. Nyquist tends to be spot on. The simulation, because it's a simulation, it's an approximation, so it's not going to be maybe as accurate as you'd hoped, but that's how it's come out. But it's still very close, isn't it? 2.1, close numbers. So let's just cancel that. Now let's go back to our PowerPoint. So we've got this as 2, and the other one is 2.1. So they're both quite close. And there's some numbers now for getting the PI gains. It's 0.45 Ku, and the TI is Pu over 1.2. So we're going to use that one for Cycle-Nichols. And for this gives you a gain margin of about 2. You can see this is a gain margin 2 design because it's 0.45. And the Nyquist-Lubin's got a bigger gain margin. It's more like gain margin of 3, so this is a slower controller. And this is so 0.3 times KU, and TI is 2.2 over PU. So they've got a bit of discrepancy in their methodologies here. But we can use these formula now to compute the controller gains. And we've just done this test here. We could also have measured off that graph. Let's have a look at it. So this one, we could have measured off this. Let's put this back up to 2.1 for a second. I could have measured off this, the ultimate period. So I would measure, say, from there to there, and there's 1, 2, 3, 4, 5 of them. So you could take an average of those 5. To get these numbers here and here, if you click on this little button here, you can move, I'm too quick for my mouse, you can then move these along until you get there. So that's giving you the time, 3.27. You can move that one to, say, there. That's giving you 9.8. So the difference between those two is giving you 1, 2, 3, 4, 5 PUs. So that from that divided by 5 will give you PU. That's a sort of method for getting PU of these graphs as well, and that should be quite similar to, going back to our Nyquist plot somewhere, should be quite similar to, this is the frequency here, so it'll be 2 pi over 4.8. So those two numbers should come out quite similar. So we've now got these little formula that we can stick into, and we know what these numbers are now. And so when I stick my numbers in, my Nyquist gain comes out as 0.9, and my Ki is 0.81, and my Nyquist gain is 0.62, and my Ki is 0.21. So you can use, now remember, you can use these formula to compute these. Remember, the controller gain Ki is given by Kp over Ti. This Kp over Ti is the value for Ki. It's the same as we had here. I suppose I could copy this. I did a little copy just to remind ourselves what we're doing here, and paste this in here, and paste it down there somewhere. There we go. So to get there, this will be Ti in that particular case. So Ki is Kp over Ti, where Ti we've got from these little tables here. For Ti, Pu, can work out Pu, and then we can stick these numbers in to get our gains. So that's then given us our Nyquist gains and our Nyquist-Lubin gains. It's not easy to say Nyquist-Lubin, is it? But anyway, we have. So we've now got our complete set of gains now, which are for gain margin 2, gain margin 3, gain margin 4, Nyquist, Nyquist-Lubin, and what we're in task 4 now, we're going to run these as simulations to see what they look like. Right, so we're now on to task 4, which is to run simulations now of our design controllers using Nyquist and Nyquist and Nyquist-Lubin, and these are going to be simulations. So we're going to use our model and these gains to look at the type of transient responses we get from the system. So that's going to involve looking at this feedback control system and putting these, we haven't got any derivatives, so just putting these two gains into the PI controller in Simulink and looking at the transient responses. So we can do that. So we load in the PI controller program, which is called closed loop PID sim. So again, you can get this off Blackboard. That's closed loop PID sim, and then you put in your gains. So the first gain is going to be 0.76 and Ki is 1.25. This is Nyquist now with gain margin 2. So run this. and just get rid of this, switch this off. So here's our Nyquist gain margin 2, and if we want to see what the peak overshoot is, we can use this little trick here. Click on that and move this onto the peak, just by moving that along a bit. There we go, and the peak is about 27% overshoot, isn't it? So let's just switch this off. So that's giving us like a 27% overshoot with gain margin 2, which is what you expect. You expect about 25-26% overshoot with gain margin 2, and a little bit of oscillation to it. If we go from gain margin 3, then the gains here have come down to 0.57. You can't use a comma. 0.57, and this one comes down to 0.98. If we run this one now, it says gain margin 3. We get much less overshoot. That's 20%. So it's about, we can have a look what it is exactly, shall we? It's about 11-12% overshoot. This has got about a 12% overshoot. So should got to get again. So this one's got about a 12% overshoot. So it's reduced the overshoot, and this 10 to 12% overshoot is good for flight control. This gives you a fast response, not too much overshoot and not too much undershoot. So it just pulls up and pulls in. A little bit less would be nice, 8%, but not too bad, that one. Again, if you want to copy these, remember, you can go to File, Copy to Clipboard, and then paste them into your report. So next one is gain margin of 4. So this one tends to give a non-overshooting response. This is 0.38 as the gain, and KP has 0.625. And if we run this one now, this gives us a non-overshooting response, quite fast. That's not too bad, almost like critically damped. You could say gain margin of 4 isn't exactly that, it's not far off. So gain margin of 4 won't tend to give you any overshoot, just sort of nice and damped, but not too slow either. So again, you could copy that one. Now if we look at our Ziegler-Nichols designs, the proportional gain was 0.9, and the integral was 0.81. This is more like a gain margin 2 design, so we're expecting a bit more overshoot on this one. Let's see if we get to work. So again, let's see what sort of overshoot we've got, shall we? It's not quite as good, this, is it? If we move this along a bit, it's giving us something like, it's only giving us 10% overshoot, isn't it? So it's giving 10%, a bit of undershoot as well. Got quite a bit of undershoot here. So, so Ziegler-Nichols is not bad, but it's not as nice rounded a curve, is it? But it's because it's got this bit of undershoot here. But it wouldn't be a bad set of gains to start off with. You could tune this arguably to get something quite good within a few minutes. So there's your Ziegler-Nichols gains. And the Nyquist-Lab one, that's more designed for gain margins, gives you gain margin of about 3 or bigger. This only got a proportional gain of 0.62 and an integral gain, which is a bit low in my opinion, 0.21. So it's going to this looks a bit low. If we run this one, we get quite a sluggish response here. This is 1 here, so it's coming up quite nice getting the proportion, but then sort of dips away because that Ki is a bit low. So it gives quite a slow response. So Nyquist-Lab tends to give you a slow response. Ziegler-Nichols a bit faster, but the Nyquist ones can give you slightly nicer results. So there's our simulation now. We've got we've tried out those out, and we've had a look at how those work. So our final task now is to compare now our simulations with the real results. So I've now gone into my garage and I've set the equipment up as carefully as I can, and I've put these gains now into it, and then I've obtained transient responses for those. So there'll be a video now on this here. Right, so now we're on to the practical results, and just remind you what's going on here. The red line is the set point, the green line is the output response, and the blue line down here, when it reappears, is the input U. So there's our three signals, and we're going to go through now the different results. So the first one is associated with Nyquist. So this one now is the Nyquist with a gain margin of 2, and to get that one I'm going to put in the gains. So it's 0.76 and 1.25. Now, and the 0 for this. Now we're looking for something like a 25% overshoot here. So there's a bit of overshoot and undershoot. Probably in this case is a little bit over 25%. So it's not bad. It's quite similar to the gain margin of 2 in our simulation, but probably just a little bit more overshoot than we'd anticipate. We'll just watch 2 of these. One of the things about a transient response is that they can look different from run to run. So we'll just watch 3, shall we? So we can see, and we can sort of get an overview of what we think. So look, that one didn't have as much overshoot, did it? Let's see what this one does. So you can see, that's a typical one now for Nyquist, gain margin of 2. So next one we're going to go for is Nyquist now with the gain margin of 3. So with Nyquist gain margin of 3, we're going to reduce the gains a bit. So it comes down to 0.57 and 0.93 and 0. So this is now Nyquist gain margin 3, slightly less gains, less overshoot. So this time we're expecting about a 10% overshoot. So this is about a 10% overshoot. So this one's more or less in line with what we were expecting, really. So let's just watch 3 of these, shall we? We've got the second one now. Second one's probably a bit better than the first one. But you can see it's consistent, this one. It's something like a 10% overshoot. I'll just do one more, shall we? You can see there's a bit of noise going on, not much, but a little bit. Last one now, and this is Nyquist gain margin of 3. It's my favourite design, gain margin of 3. It's got a nice little response there. So that's about 10% overshoot. So next one we're going for is Nyquist gain margin 4. This has got a lower gain, and well, probably gain margin 4, you're going to lose your overshoot. So it's quite a low gain this time, 0.38. It's half of what the gain margin 2 was. And this is 0.625. Somebody's just making a phone call now, but never mind, I'll just talk over the phone call while somebody else answers it. So this is gain margin of 4 now, and we're looking for a non-overshoot. So this has got a non-overshoot, isn't it? Quite clearly, it's non-overshooting. It's a little, it's not bad, is it? It's not bad. It's a little bit light just here, isn't it? Of a good track. But let's have a look at 3 of these. You never know what the next one might do. This one's come up better, isn't it? So you can see, this is a gain margin of 4. So gain margin of 4 now tends to give you a response that doesn't have any overshoot on. It's slower than the others, but doesn't have any overshoot on. So there's our 3 of those. What we're going to move on to next is the Ziegler-Nichols. So next one now, this one now is our Ziegler-Nichols tuning, and so let's put the gains in for Ziegler-Nichols. Ziegler-Nichols has an approximate method, but it's going for roughly a gain margin of 2, and this is 0.9, and Ki is 0.81, and Kd is 0. So this is our Ziegler-Nichols now with design. So it's not bad. It's not the greatest, is it? It's come up quite well here. Come up quite well, but it's done this bit of undershoot here, which is a bit unfortunate. So not too bad, but not as good maybe as our Nyquist gain margin 3. I still think that's my best one. So it's a little bit down, not too bad, but not as good. Just watch for one more. So this is our Ziegler-Nichols design. The gain, proportional gain is a bit high, probably. Ziegler-Nichols tends to have a big. You can see it's not awful, is it? There's our nice Ziegler-Nichols. I met Nichols once in Las Vegas. But that's a different story. So our last one now is Nyquist Lab. These must be from Germany or something. So these have got lower gains because they go roughly for a gain margin of 3, but again approximate method. So proportional gain is 0.62 and the integral gain is a bit low at 0.21. So this is our Nyquist Lab design. We can compare these. The first time round it has a little problem with it, so we'll just ignore this one. Wait for it to come in next time round, it'll be a better result for us. In a second now, here we go. It'll start more or less tracking this time, hopefully. Here we go. So this one tends to have not quite enough integral, so it's a bit slow here pulling up. It does pull up, but it's a bit slow doing it, isn't it? But this is what our simulation was telling us as well. That this is the type of response we're going to get from the Nyquist Lab. So there's a good correlation between the simulation results and the practical results. You can see it tends to sort of come up, go down, then slowly pull up. Just about tracks at the very end. We'll watch it one more, shall we? Now, last thing I wanted to do, this is an interesting little trick which you can do. You can't always do this in real systems, but on some systems you can. And that is, we can look at the Ziegler-Nichols continuous cycling to get Ku. Remember, this is the gain now at which the system goes marginally stable. And this, from our Nyquist plot, was 2. So if our model's good, when we do a continuous cycling, it should go unstable, or marginally stable, around 2. So if we try some different gains now, let's start off with 1, shall we? 1, 0, 0. So this is our continuous cycling now, and we're looking for when it goes into a marginally stable, so that's clear that's stable. So that's not interesting. Okay, let's go for 1.5, 0. So this is 1.5 now. Remember, 2 is our number we think is going to go up. So this is 1.5. So it's a bit more bouncy, isn't it? But you can see it's still decaying with time, so it's still stable. So you go for K, 1.8, 0, 0. This is 1.8 now. So we're getting closer to the 2, which we predicted. Let's have a look at 1.8. So 1.8 it's more oscillatory, isn't it? But it still isn't unstable. So if we go for K as, let's try 2, shall we? 2, 0, 0. This is 2 now, this is our predicted value. Let's see what this one does. So if you look at this is pretty much close to now a limit cycle. It's very, very close to it. That's where the amplitude along here is more or less constant. You can see it's just maybe slightly decaying, but 2 is quite close. So it's indicating now that our model is quite good, because in our Nyquist plot, this was saying it was going to be about 2.03 or something like that. So, and that's 2. So if we try K as, let's say, 2.1, just to see what that does. This is just a little bit bigger. This is 2.1 now, so you can see at 2.1 it's definitely like a limit cycle, isn't it? So if not slightly going away. So you can see the answer is quite close to 2. I just put another K in of 1.9. just for you to see. And this is 1.9 now, which is just a little bit below 2. Obviously 1.9 is below 2, you know that. And this is 1.9 now. So with 1.9, it is still, you can see it's still decaying, isn't it? It's just about decaying. It's very, very slowly decaying. Whereas that 2, 2, 0, 0, this is now giving very close to being marginally stable. So it's indicating that our model that we got was actually quite good, because it was able to predict when this system would limit cycle at 2, and the actual system does limit cycle at 2. And that's always a good check. If those two are quite close to each other, you've got a good idea then that the model and the real system are not far off each other. So there's your practical results now, and you can compare these practical results with the simulation results you've obtained in MATLAB Simulink, and you can then see how similar they are and draw some conclusions from those, or discussion and just conclusion, I suppose. So that's the results. Right, so this is just a bit of a review that I've done of the various results. So we've got the things to look at: task 1, open loop step response and modelling; task 2, the PI controller designs and simulation; and then there should be task 5, shouldn't it? But anyway, task 5 was comparing the simulation results. Seem to have gone wrong, you know. I don't know what I've done now. So seems to have deleted a file. Anyway, so let's have a look at them. This was our task 1. Here was our real data here, and here was the data when we transferred it into MATLAB, and then we did a model and we got the transfer function out: 1.55 of 0.6 s+1, time delay 0.4. And you can see the fit was good, so we got good fit on that. Then we did Nyquist design, and these are the Nyquist designs now for gain margin 2, 3 and 4, and these are the real-time results, which I've got as screen dumps off the video, and you can see there's a good correlation between these. This one's got, you know, overshoot, undershoot. This one's got a bit of overshoot, a little bit of undershoot, and this one's got no overshoot at all. So there's a good correlation now between our Nyquist simulations and our different Nyquist designs for different gain margins on the real system. Then I've gone on to do the Ziegler-Nichols. So this is the Ziegler-Nichols design and simulation. This is the Ziegler-Nichols in real time. So again, you see the underlying shapes and characteristics of the curves the same. And similarly for Tirias-Lubin, same sort of response shapes here. This is my simulation for gain of 2. It's just about margin, or 2.1 actually. And this was my 2 on the rig. So you can again see there was a good correlation between the point of the ultimate gain on the rig and the ultimate gain on the simulation were very similar. So I thought they were handy little graphs for you to have a look at in terms of making a final assessment of how the experiment went. And what you need to do is discuss these, and discuss these, and then draw some general conclusions about the bigger picture about the lab. And we're now done. So that's handy, isn't it? So you can now go off and start thinking about it and thinking about writing it.